Hello everyone and welcome back to Diksha Karnataka YouTube channel. Your second PU midterm exam is on your head. So we are revising all the chapters. Important questions, only the important questions and some practice questions based on your previous year questions and the model question paper which is released by PU board. So we are going to discuss today moving charges and magnetism, another important chapter, another super important chapter. Also we are going to discuss what are all the questions that might come from this chapter. So don't go anywhere. If you are preparing for your midterm, then this is the place where you should be. So let's start with the chapter. First of all, let us look into the marks distribution of the chapter. 1 mark question is coming as MCQ, no fill in the blanks from this chapter as well. If you remember in our previous chapter current electricity, there was no fill in the blanks question. From this chapter also there is no fill in the blanks question, only one MCQ question, and mostly either remember or HOTS question. Okay, HOTS question means little bit tougher, remember means little easy. So both type of question might come from this chapter. In short answer type 2 marks question, okay, most probably it will be a 2 mark numerical problem. There is a possibility, very small possibility, that there will be a theoretical question as well, but 2 out of 3 model question papers suggest that there will be a numerical question based on this chapter. So we will solve a few numerical questions, 2 mark question, only 2 mark question. So you have to know the formula, put the values, you will get the result. Very simple, right? And it will be either understanding or application based question, so medium level question. Okay, now short answer type 3 mark question, there will be one 3 mark question as well from this chapter, either remembering or understanding, so easy question. Okay, in long answer type question it will be only long answer type question, no numerical question is coming from this chapter. So only thing that you have to prepare is long answer type questions, understanding or application based questions. So questions generally all the questions from this chapter, long answer type question chapters, can be predictable. They have added one new question in your model question paper. We will show what is the question and possible solution to that as well. Otherwise this is a very scoring chapter. You don't have any long hard numerical problem coming from this chapter, so you can score good from this chapter. Total weightage of the chapter is 11 marks. Let's see with the MCQ questions. Okay, a moving coil galvanometer can be converted into a voltmeter by connecting. So how can you convert a galvanometer into a voltmeter? So basically they are testing, if you know the knowledge, to convert a voltmeter into a convert a galvanometer into a voltmeter, my mistake, you have to add high value resistance in series. Okay, so the answer will be a high resistance in series with the galvanometer. So read the options carefully one by one and then be sure which one is the correct answer. See, high value resistance is given in option C as well, but here it is given as parallel. So by mistake if you answer this, you will be wrong. So high resistance in series with the galvanometer. Simple answer. Now next, move on to the next question. This is little bit tricky question. The physical quantities related to magnetism are listed in the column 1 and the dimensions are listed in the column 2. Identify the correct match. So basically it's a matching question. They have given you 2 columns. Each column has 3 fields. Okay, magnetic field, magnetic permeability, magnetic moment. Okay, and the corresponding dimensions are given in the second column. You have to match it. Once you have matched, then you have to check which one is the correct answer. Now how can you answer this question? So let us start with magnetic field. How can you remember the dimensional formula for magnetic field? So for that we have to use some familiar equations from where we can derive. So first of all, the familiar equation, we know that from Lorentz force, the force acting on a moving charge with a velocity v is given by QVB. Okay, there is a sin theta term, but sin theta is dimensionless, unitless, so we are not using that. So QVB is the formula. Now what is the dimension of force? Force, we know that mLt to the power minus 2. This is the most known dimension. If you are not familiar, you have to remember this. What is the dimension of charge? charge can be found by charge by time is basically ampere. So charge dimension for charge is nothing but ampere t. At q is equal to at, that is the dimension for charge. So a t is the dimension for charge. Now velocity, what is the dimension for velocity? Velocity's dimension is L t to the power minus 1 meter per second, right? So meter is L, per second is t, and b's dimension we are trying to find, so we are keeping this b separated, right? Now from this side you can cancel L cancels. Now t to the power minus 1, so these two will cancel automatically. So we can say that b dimension for b is nothing but m t to the power minus 2, and this a will go to the other side, a to the power minus 1. Okay, now let's see which one is correct. So from magnetic field we can see that the correct answer is this. So this is the correct answer for magnetic field. Okay, so correct answer for magnetic field is either you write like this or you write like that, whatever way you are comfortable. Okay, so for 1, correct is C. Now magnetic permeability. Magnetic permeability is easy to remember. It is the most difficult one to remember. Okay, so ml t to the power minus 2 a to the, if the expression is a little difficult, little bigger, that will be the dimension for magnetic permeability. Okay, you remember like that. Okay, ml t to the power minus 2 a to the power minus 2. There is a to the power minus 2 present in the expression for magnetic permeability. Now for magnetic moment, whatever is left, that is magnetic moment. Okay, L square A. Okay, L square A, you can find the formula using another equation, but otherwise it is easy to remember. L square A is the magnetic moment. It's the easiest formula to remember. Okay, so magnetic field you can calculate. Okay, even if you remember, that is fine. If you don't remember, then you can calculate. Okay, magnetic permeability is the it is little longer, okay, difficult one, so that will be the biggest one, so that is the magnetic permeability. So we can see that 1 equals to C, 2 equals to A, and 3 equals to B. So 1 equals to C, 2 equals to A, and 3 equals to B. So correct answer is option D. So if you see there is another one where B is equal to C is given, 1 equals to C is given, but here the other two options are wrong. So correct answer will be option D. Be careful while answering such question. You have to check all the options are matching or not, right? So once all the options are matching, you can easily answer this question. Now let's look into another matching based question, but this is little bit question. Length is bigger, question answer is easier. Okay, what is the question? A charged particle of charge q is moving in a uniform magnetic field. The angle between the velocity of the charged particle and the magnetic field B is theta. The trajectory of the charged particle varies with angle theta. Match the following table by choosing the appropriate trajectory traced by the charged particle for different possible values of angle theta. Okay, so they have asked you to find the trajectory based on which the trajectory will be chosen. So we know that if the angle theta is 90 degree, it is a circle. This is the first one that we remember. Okay, if the theta is 90 degree, then it is a circle. Okay, there is the condition. The magnetic field and the velocity vector should be perpendicular to each other so that it is a circle, right? So first of all, we can easily identify that, and we can say this is the first one. Okay, so for 3, option A is correct. Now for angle theta equals to 0, okay, it will be a straight line. No force is acting on the particle. It will continue to move in the same direction, right? So we know that F is equal to QBV sin theta. Theta 0 means force 0. Force 0 means no force is acting. So it will be a straight line. Okay, and you should remember that any angle between 0 and 90, it will be a helical motion, helix motion. So this is also option C. All the options are found correctly. So now let's see which one is the correct. 1 is equals to B, 1 is equals to B, 2 is equals to C, 2 is equals to C, 3 is equals to A. So correct answer is option B. Okay, in this case, correct answer is option B. Be careful while attempting these questions. So you need to be careful that theta equals to 0 means it's a straight line, theta is equal to 90 means circular motion. Any angle between 0 and 90, it is a helical motion. Okay, so even if you don't remember the helix one, you can still find for theta equals to 0, it's a straight line. For theta is equal to 90 degree, it's a circle. So you can still answer that question. Okay, it is an easier question. Now, next question, the Lorentz force is the force on a charged particle moving in a region containing, okay, so now the exact form of Lorentz force, as we know, is given by QE plus QV cross B, right? This is the formula for Lorentz force. So Lorentz force is there when there is a magnetic field as well as electric field. For both the fields are there at any angle. The angle between B and E is immaterial. So as long as they are present, any magnetic field or any electric field, any one of them is present or both of them is present, then Lorentz force is applicable. So only electric field is not correct, only magnetic field is also not correct, both electric and magnetic field is correct. Okay, and D is only crossed. Electric and magnetic field crossed means they are at perpendicular, which is not correct. At any angle it will be applicable. So correct answer is option C in this case. Okay, now let's move on to the next question. The force on a charged particle, again the force on a charged particle moving in a magnetic field is maximum when the angle between the velocity of the charge and the magnetic field is. So moving on a force acting on a charged particle QVB, magnetic force actually is sin theta. Okay, so the force will be maximum when sin theta is maximum. So what is the maximum value of sin theta? Maximum value of sin theta is 1. At what angle sin theta becomes 1? At 90 degrees sin theta becomes 1. So the force will be maximum at an angle of 90 degrees. Simple question, simple answer. Now let's move on to the 2-mark question. Now this is a numerical question. So you need to remember a few formulas for these questions, 2-mark numerical questions. If you are able to answer other questions, you can skip these 2-mark numerical questions, but these are very easy questions, only one formula, one equation. If you apply, you can answer it correctly. Okay, for example, this question, a long air, this is a very common type of questions. Okay, this common type of questions, this almost comes in every year. Okay, a long air core solenoid of 1000 turns per unit length carries a current of 2 ampere. Calculate the magnetic field at the midpoint on the axis. Okay, so what is the question? A long air core solenoid. Okay, so basically we know that magnetic field at the center of a solenoid is given by mu naught I, okay, Ni, sorry, mu naught Ni. For one core, one coil, one turn, it is mu naught I. For multiple turns, it is mu naught Ni. Okay, here N is the number of turns per unit length, right? And mu naught is, if you still don't remember, 4 pi times 10 to the power of minus 7. Okay, mu naught is 4 pi times 10 to the power of minus 7. Mu naught by 4 pi is 10 to the power of minus 7. Okay, this is also a constant like epsilon naught, if you remember, right? So now here we have to insert the values. They have given directly mu naught, we know 4 pi times 10 to the power of minus 7. N is given by 1000. Okay, current is given by 2 amperes, so 2. So just multiply 2 4 is 8 pi times 10 to the power of minus 7. 1000 means 10 to the power of 3. So it will become 10 to the power of minus 4 Tesla. SI unit, everything is in SI. Then you can write the unit of magnetic field as Tesla. Let's see the answer. Answer is 8 pi into 10 to the power of minus 4 Tesla. So we have solved it correctly. So you can see that this is only a 2-line solution. Okay, so if you know the formula, it is very easy. 2 marks guaranteed. Now let's look into the second question. A moving coil galvanometer gives a deflection of 10 divisions when 200 microampere of current is passed through it. Find the current sensitivity of the galvanometer. So what is the current sensitivity? Definition of current sensitivity, okay, is given by number of division divided by the amount of current passing through it. Now it is a microampere, so microampere means 10 to the power of minus 6. Okay, so 10 divided by 200, 10 to the power of minus 6, or 10 divided by 2 times 10 to the power of minus 4. So I have taken these two zeros and I have adjusted against minus 6. So just you have to be careful. 5. So 5 times 10 to the power of 4, or you can write 5, 0, 1, 2, 3. Okay, because it's a microampere, the sensitivity is very high and its unit is 10 ampere inverse. Okay, ampere inverse. I guess the answer for this is I have calculated it wrongly. So correct answer is this. Okay, this is not the correct answer. Now next question, another 2 more question. This is not a numerical question, so numerical questions are over. So that is a good relief. There will be no numerical questions for this chapter. When does a current carrying conductor placed in a uniform magnetic field experience maximum and minimum force? So what is the question? Current carrying conductor placed in a uniform magnetic field. So force acting on a current carrying conductor placed in a uniform magnetic field is given by BIL sin theta. Okay, so BIL sin theta, and we know that the force will be maximum when sin theta is equals to 1. So that is force theta equals to 90 degrees. So when the current is being carried and the magnetic field, the direction of current carrying wire and the magnetic field is at 90 degrees, then the force will be maximum. So in this case you cannot just simply write theta equals to 90 degrees. What is theta? You have to explain that because it's a 2-mark question. So you have to write when current is carried at an angle 90 degrees with the magnetic field. Or you can write current is perpendicular to the magnetic field. That is also fine. And from this you can say what is the minimum when angle is, same answer, angle is 0 degrees. Okay, force will be minimum, this is maximum, this is minimum. Okay, for minimum theta will be 0. So you have to write the same statement with angle theta equals to 0 degree. Okay, simple, easy question. Now write the expression for magnetic force per unit length between two long straight parallel conductors carrying current. Give the nature of the force between two parallel conductors carrying current in the same direction. Okay, they may ask you another opposite direction. Okay, now here the expression is given by mu naught Ia Ib by 2 pi d. Here either you can declare all the variables or you can simply draw one diagram. Okay, one wire is carrying current Ia in this direction, another wire is carrying current Ib in this direction. The distance between them is t. Okay, simple. If you draw this diagram, fine. Or you have to explain Ia is current through conductor A, Ib is current through conductor B, D is the distance between them. I guess if you draw this diagram, all those things are being taken care of, so you will get full marks. If you don't draw this diagram or don't declare the variables, they might deduct marks for this. Okay, and what is the nature of force? Nature of force, for that I have given you both the answers. Parallel currents attract and anti-parallel currents repel. So if the current are being carried in the same direction, they will attract. Okay, they will attract each other. And if the current are anti-parallel, that is one is carrying this way, another is this way, then they will repel each other. Okay, parallel currents attract, anti-parallel current repels. Okay, this is simple. Now let's move on to the next question. State and explain Biot-Savart's law with a suitable diagram. So diagram I hope everyone knows. So there is a curve like that. You take a small portion of this, then you take this point P, some point P. Okay, then you say, okay, this is the length DL. Okay, this is the direction of current. You say this is the vector dl, this angle is theta, okay, this distance is r. Okay, now what is the current flowing through this conductor is I. Okay, so what is the Biot-Savart law? Biot-Savart law tells you the magnetic field dB at this point due to this current element. So first of all, you have to write the current magnetic field at a distance r from a current element dl is given by dl is magnitude of the, you are writing in terms of magnitude of the magnetic field is directly proportional to the current element dl. Okay, magnitude of the current element dl, magnitude of the current I, current is a scalar quantity, so dB is proportional to I, then dB is inversely proportional to 1 by r square, and dB is proportional to sine of the angle theta. Okay, this is the Biot-Savart's law. Combining them, we can write dB equals to mu naught by 4 pi I dl sine theta pi r square. Okay, this is the Biot-Savart's law. Since it is a 3-mark question, you have to write up to this point. Okay, so only these 4 points are sufficient along with this. Okay, and this circuit along with this diagram, if you draw it, you will get full marks. Now, next question: derive an expression for angular frequency of revolution for a charged particle moving perpendicular to a uniform magnetic field. Or this question sometimes comes in a second form, or obtain an expression for the radius of circular path taken by a charged particle moving perpendicular to the uniform magnetic field. So either they will ask you to find the angular frequency, nothing but angular frequency same as angular velocity omega. Okay, or sometimes they will ask you find the radius. Same strategy and equations are same, only thing the values that we are finding are different. So what is that? We know that force acting on a charged particle is given by QVB sine theta. Now if the angle, they are perpendicular, okay, so if they are perpendicular, both cases they are perpendicular, so in that case theta is 90 degree. Okay, so we can write that F is equal to QVB. Okay, now when the force is acting on the charged particle suppose is moving in this direction, magnetic field is in this direction, it will experience a force that will tend to make it move in a circular path. Okay, so magnetic field, suppose the object is moving in this direction, magnetic field is into the page, it will tend to move in a circular path. And then what is needed for circular motion? The only thing that is needed for circular motion is centripetal force. Now centripetal force is a force which has to be provided by the interaction between the field and the charge. So basically this force, Lorentz force, will provide the required centripetal force. Centripetal force, whenever there is a circular motion, some force, external force, some force, the interaction force actually providing the required centripetal force. So centripetal force should be, what is the centripetal force? We know that centripetal force is mv square by r. Okay, that force should be equals to QVB. So basically QVB or the Lorentz force is providing the centripetal force. Now let's simplify this. One of the V will be cancelled. So you can write that V equals to QBR by M. Okay, QBR by M. Now for question number 1, that is this one, suppose this is 1 and this is 2. Okay, for question number 1, from here we have to use the formula that V equals to R omega. V equals to R omega. This is a rotational motion concept. I hope you remember. So V is equal to R omega, or R omega is equal to QBR by M, or R cancel. So angular frequency omega is equal to QB by M. This is the first part. Okay, up to this part is common. After that, if they ask you angular frequency, you can find it like this. Okay, And if they ask you to find the radius, from here radius is r, simply mv by qb. In this case you don't need to substitute v, you can keep v as v. This is for part 2 or question. Okay, so either you have to substitute v is equal to r omega and calculate this, or from here you can use r equals to q mv by qb. One of these two questions is very probable in your midterm and as well as in your final exam. Okay, one of these question is very probable. Next, what is Lorentz force? Write this expression and explain the terms. So what is the Lorentz force? Lorentz force is a force acting on a charged particle when it is moving in a electromagnetic field. Electromagnetic field means both electric field and magnetic field are present. And what is the expression for Lorentz force? We know that it is Q E plus Q times V cross B. Okay, or you can take Q common, E plus V cross B. Okay, this is the expression for Lorentz force. Okay, so this is the answer. And then you have to mention the terms. F is Lorentz force, E is electric field, V is velocity of the charged particle, B is the magnetic field. Okay, that things you have to mention to get the full marks. Okay, so I am just mentioning what you have to write. And Q is the charge of the charged particle. Okay, charge on the particle. So these things you have to mention. Now, how can you convert a galvanometer into a voltmeter? Explain with diagram. Now, galvanometer to voltmeter, galvanometer to ammeter are very common and important questions. Okay, and very often asked in your midterm question. So let's see. To convert a galvanometer into a voltmeter by connecting a suitable high resistance in series with it. So if there is a galvanometer, okay, and there is if we add a high resistance in series with the galvanometer, then it will become a voltmeter. So this will behave like a voltmeter. Okay, now the current here is Ig. Okay, so we can say that the voltage across the entire thing is basically V equals to galvanometer resistance plus external resistance, shunt external high value resistance times Ig. V is equal to IR. Here R is G plus R. So what is the value of R? Basically we are interested to calculate the value of R. Be careful what you are interested at. Some people, most of the time I have seen people have shown the value of Ig. Ig we are not interested here. We are only interested in the value of R. So R is basically V by Ig minus G. This is the value of R. Simple. Okay, so you can in some cases if there is a numerical question on based on this formula, you can directly use this formula. Okay, now let's look into the second question. How can a galvanometer be converted into an ammeter? Explain with diagram. So a galvanometer can be converted into an ammeter by connecting a suitable low resistance S in parallel. It is called a shunt, okay, with it. Either you can mention a low value resistance or you can mention a suitable shunt. Both are okay. So in that case, what is galvanometer? Galvanometer is G. Okay, now here what you are doing, you are connecting a low value resistance shunt with it. Suppose the current in the circuit is I. Okay, the current in the galvanometer is Ig, current in the shunt is Is. Okay, then we can write that from the parallel combination thing, Ig equals to I times S by G plus S. Okay, from here you have to calculate the value of S. Okay, or you can leave from at this point also, but it will be better if you can show what is the IgG plus IGS equal to Is. Okay, or Ig G equals to I minus Ig S, okay, or S equals to Ig G divided by I minus Ig. Okay, so this is the expression for shunt resistance. If you answer this up to this point, you will get full marks. So you remember what you have to show. Now how I written this? Ig is current through galvanometer equals to total current I times current you are measuring through galvanometer, right? So the resistance, first resistance should be the opposite one. That's how you can remember. S divided by the total resistance, G plus S. Okay, when I was a student, this derivation was very important for us. We have to remember the derivation, but nowadays this derivation is no longer coming, so you don't need to remember this derivation. Okay, you can simply use this formula and calculate. This is called parallel resistance formula. If you are studying engineering in future, then you have to be careful, and this formula will be very useful for you. Now next, derive an expression for the magnetic field at a point on the axis of a circular current loop. Very important derivation. Here what you have to do, you have a circular current carrying loop, carrying a current I, okay, and you have to find the magnetic field at this point P. Okay, derivation I am not going to do, derivation is there in the in your book. Okay, what you have to do, you have to take this distance, this radius is r, okay, and due to this current, whatever is the magnetic field at this point, okay, there are a lot of formulas. You have to take a small portion here, okay, and then you have to calculate the magnetic field. Okay, very important question. Okay, from there you will get two components, and you have to apply Biot-Savart's law. One is along this, one component will be along this, one component will be along this. So this will be your dB. Now remember that some students, I have seen students say this angle from Biot-Savart's law, this angle is 90 degrees, so theta equals to 90 degree, and then again they use this angle also theta. Okay, so if you are using, that's why I have drawn this diagram. This angle is for Biot-Savart's law, this angle is 90 degree, fine. So if you are using this angle as theta, then do not write this angle as theta, you use a different symbol. There are a lot of symbols available, use this for phi. Okay, so while you are derivating, I have seen students, they are following certain publishers' books. I know that name of the publisher books, I will not name that book. They study directly from there. They have mentioned theta in both cases. Student write theta in both cases. One case they write theta equals to 90 degree. In the second case, they take the theta as a arbitrary value and they do the integration, they do substitution, etc. So how can one theta, one place 90 degree, another place is non-zero? Not possible, right? There are different symbols available. Use different symbols. Okay, so if you are not aware, you have to use different symbol, and the derivation is given in your book. I hope you have practiced that. This is the easy derivation, not super hard, so that's why I am not doing it. Now derive an expression for force per unit length on a two infinitely long thin parallel straight conductors carrying current, and hence define ampere. This is a very, very important question. Okay, so that's why again, two current carrying conductor, one is carrying current IA. I have drawn this diagram. Suppose the second one is carrying current IB. Okay, now first you have to find the magnetic field due to this current carrying wire here, then apply the formula for force acting on this Bill sin theta. Sin theta is 90 degree, so theta will be 1, and then you have to apply the force per unit length. So it will be coming out to be FAB equals to mu naught by 2 pi, okay, IA IB by D. Okay, if you remember the distance between them is D, you have to derive this. Okay, derivation is easy. Again, first you have to find the magnetic field due to this current carrying wire here. Okay, then Bill sin theta. Okay, then you have to take some length, arbitrary length. length L. Okay, and then at the end you have to divide it by L to find the force per unit length. Okay, you have to mention force per unit length. Okay, so that is what is important. And magnetic field due to a single current carrying wire is mu naught by 2 pi current I by distance d. Okay, this is the formula for current carrying wire. Okay, so and then you have to add BIL sin theta. So you will get for BA it will be BA IA. Then you can multiply and you can calculate the equations, right? Now what is the definition of ampere? That's where I see most students actually falter. Okay, most students write wrong answers. What is the definition of ampere? To define ampere from there, what you have to assume that let's say IA equals to IB equals to 1 ampere, 1 unit. Okay, so first of all let's say IA equals to IB. Okay, FAB equals to 1, not 1, sorry. So first let us understand this definition. IA is equal to IB is equal to 1 ampere. Okay, D is equal to 1 meter. Then what will happen? Then what will happen to FAB? FAB will become mu naught by 2 pi. Okay, this is 1, this is 1, this is 1, so all of them are 1. Now what is mu naught? Mu naught is 4 pi times 10 to the power of minus 7 divided by 2 pi. So it will be 2 times 10 to the power of minus 7 Newton per meter. Okay, so this is the force per unit length. So how can we define ampere? When two equal currents flowing through conductors kept at 1 meter distance, two equal amount of current carrying parallel wires kept at a distance 1 meter, if the force acting between them is 2 times 10 to the power of minus 7 Newton per meter, then the current is equals to 1 ampere. This is how we define ampere. Or you can say directly also, if two current carrying wires carrying 1 ampere current through them kept at a distance 1 meter, then the force acting between them is 2 times 10 to the power of minus 7 Newton per meter. Force per unit length is Newton 10 to the power of 2 times 10 to the power minus 7 Newton per meter. So this is how you have to define ampere. Most students do not define ampere properly. Some students skip it. It has 2 marks. Okay, if you are lucky, maybe 1 marks. If you are unlucky, 2 marks. Okay, and most students do not define ampere from this derivation. After the derivation is over, derivation part, up to derivation part, most students do it properly. After the derivation is over, they are unable to define ampere. That's why I have taken this question. This is very important question, and don't miss out on the definition of ampere. Okay, now this is a new question recently added to one of your model question paper. Let's see this question, then we will see the answer. What is the principle behind the working of a moving coil galvanometer? With the help of a neat level diagram, obtain the expression for the angular deflection produced in a moving coil galvanometer. Okay, so this is a little complicated diagram. You don't need to draw this much a large diagram. You can simplify this diagram with a single coil, one coil here, and this magnetic field and this deflection. So first of all, let us understand the principle. What is the principle? Principle of a galvanometer is that torque acting on a current carrying coil kept in a magnetic field. Okay, so basic principle is that when we keep a current carrying coil in a magnetic field, it experiences a torque based on the amount of current. More the amount of current, more is the torque, and if we can measure that torque, we can measure the current. Okay, torque is directly proportional to the current, and then you have to define, this is the angle phi. Okay, this is the angle with which you can measure. Suppose this is 0, this angle is phi. So the angle phi is NAB by K times I. The derivation is given in your book. You can check this answer, but I don't recommend this question. This is a new question, never came in your previous year question papers. So I don't think it will be very important, especially for your midterm. If you get time for your final PU, because the question paper pattern is changing slowly. So maybe if you get time, you can prepare this for your final exam. Otherwise, you don't need to prepare this question, especially for your midterm question. Maybe very unlucky if you are from where you are watching this video. If you are very unlucky, this question might come. Otherwise, you can skip this question. But I kept this question because it was a part of your model question paper. Right, now we have reached the end of this lecture. I hope you enjoyed the questions. If you have any questions, any doubt, don't forget to mention that in the comment. I will try to explain each and every point, every doubt that you might have. I will be back with remaining 2 chapters, alternating current and ray optics, 2 important chapters, that is ray optics and optical alternating current tomorrow if possible, and other chapters, all the other chapters I will be combining them into a single video. They are small chapters, so not required a full lecture, full length videos. So I hope you enjoyed this lecture. I will be back tomorrow.